Air navigation service providers coordinate thousands of flights a day, managing massive variables in speed, altitude, and weather. Yet the tools used to execute this complex task are often surprisingly constrained. For decades, air traffic management has operated within closed-circuit, proprietary vendor hardware. These systems function as impenetrable black boxes, locking operators into inflexible upgrade cycles and rigid operational parameters. This lack of internal visibility creates a downstream dependency. For key performance indicators and auditing, operators must rely on external, centralized European entities like Eurocontrol to provide them with data about their own airspace. You cannot dynamically optimize an environment you cannot independently audit. Relying on delayed, third-party data creates operational blind spots, preventing local operators from adjusting airspace limits to match actual daily traffic. Achieving actual operational efficiency requires dismantling this dependency. The solution is to rebuild the air traffic management tech stack from the ground up, capturing raw surveillance signals and writing the internal software to automate spatial rules locally. By engineering sovereign technical stacks, operators transition from passive consumers of vendor equipment to active managers of modern airspace capacity. Before you can write a line of code to automate flight paths, you need a flawless set of rules. Operational safety and algorithmic logic must stem directly from globally recognized aviation law. In many organizations, these rules are trapped in a fragmented web of paper documents and static PDFs. Managing complex airspace with outdated or misaligned references introduces an unacceptable margin for error. The foundational architectural layer solves this by stripping away the paper. A centralized web platform acts as a single-window relational database, indexing all ICAO regulations and annexes into a single, searchable digital source of truth. This platform utilizes a profile-based notification engine. When an international amendment is published, the system instantly pushes the critical regulatory update to the specific operational units affected. A perfectly digitized, instantly distributed rulebook serves as the structural prerequisite. Only when the regulations are standardized digitally can they be translated into algorithmic geometry. With the rules digitized, the operational requirement shifts to real-time spatial awareness. Breaking dependency on external feeds requires establishing an independent pipeline for raw surveillance data capture. This is achieved by deploying agile hardware. Software-defined radios, paired with high-gain antennas, are positioned to capture unfiltered 1090 MHz ADS-B and Mode S messages directly from aircraft. This animated diagram shows the initial capture phase. A raw radio frequency wave is intercepted and sliced into discrete digital data packets. These high-density digital packets stream directly into a custom-built, highly optimized C++ backend for real-time ingestion. Inside the engine, the data is structured using the AIXM protocol, the strict international standard for surveillance data exchange. The engine sorts the chaotic feed and tags it with proper multi-radar correlation labels. From there, the algorithms translate these sorted packets into precise plot coordinates, calculating predictive tracks across a spatial grid. This integration of custom backend processing with a real-time visualization interface forms the SDR prototype, the secondary treatment aeronautical radar system. By reconstructing the entire chain from signal to screen, the organization generates a real-time truth dataset, bypassing the latency of centralized third-party feeds. Mastering the internal processing of raw radio frequencies and asterisk data eliminates vendor lock-in. It grants the organization absolute ownership over its airspace data. Capturing the data is the mechanical step. The operational value comes from deploying that sovereign data lake into large-scale airspace analytics. Traditional airspace planning relies heavily on static, theoretical models. Planners draw routes assuming aircraft will fly perfectly rigid lines, which rarely accounts for the actual behaviors and shortcuts taken by human crews. This animated diagram illustrates that theoretical approach, a clean, straight 3D wireframe corridor representing a standard terminal arrive route. But when we overlay the historical ADS-B data lake onto this model, the reality becomes visible. Thousands of actual 4D trajectories, tracking latitude, longitude, altitude, and time, populate the space, forming a dense heat map of empirical execution. Planners can now observe the physical delta between the theory and the practice. Notice the dense cluster here, where the organic flight lines consistently bypass the sharp corner of the theoretical wireframe. By feeding this exact empirical data into a trend engine, operators can precisely calculate metrics like true runway occupancy time and identify highly specific surface congestion points. Adjusting flight procedures based on these documented behavioral trends reduces unnecessary flight miles, directly lowering carbon emissions and safely unlocking hidden capacity at the airport. Optimizing the airspace creates tighter, more efficient corridors. But this precision introduces a new vulnerability: the massive, exponential rise in commercial and private drone operations requesting access to the same zones. Assessing these requests manually against complex instrument flight procedures requires cross-referencing maps and charts by hand. It is mathematically slow, heavily bottlenecked, and highly vulnerable to human error. To automate this, we need a standard capable of exact spatial mapping. This diagram represents the AIXM 5.2 data structure, mapping the protection volume of an instrument approach procedure as a complex, transparent 3D funnel. When an operator submits a new drone flight request, the system models it as a solid geometric polygon and introduces it into the mapped environment. The C++ backend acts as a high-speed computational geometry engine. The moment the polygon breaches the edge of the protection funnel, the engine calculates the spatial conflict, illuminating the exact intersection points in red. The math is processed in milliseconds. The system logs the historical trajectory request and instantly generates an automated approval or denial report based entirely on the geometry. Translating aviation law into precise algorithmic geometry is the only mathematically scalable method to ensure safety in dense, mixed-use airspace. This diagram visualizes the architectural stack required for operational autonomy. 4 integrated layers functioning as a single unit. Standardized rules form the base. Sovereign surveillance captures real-time truth. Empirical analytics optimize paths. Algorithmic deconfliction protects volumes. Insights loop back to refine the base. Operating at this level changes the fundamental role of the organization. A modern air navigation service provider transitions from a consumer of vendor hardware to a specialized software house capable of modifying its own core systems. Maintaining this architecture requires deep internal expertise. Building and refining these systems creates a critical mass of intellectual capital, engineers and controllers who understand the data from the protocol level up. When executed correctly, the organization operates a self-reliant, high-speed ecosystem capable of analyzing its own performance and mapping its own future. Intellectual capital and data sovereignty are the foundational prerequisites for predictive, high-capacity airspace management. Building the technical stack internally ensures that the logic of the airspace remains entirely within the control of the people who manage it.